Yeah, there's the official title, Saving Math from Plato's Progeny. I think I covered Saving Math from Plato last time. There'll be some review here, but I'm trying to streamline it. But I know that most people who were here, or in Miami actually, probably have forgotten much of it anyway, so I don't think it will bore you the second time. And I've got a sexy introduction. The right angle triangle of sides 1. What is the hypotenuse? Well, we know it's the square of the two sides. So if the sides are each one, it's an isosceles triangle, then the square is 2, and the non-squared regular hypotenuse length is the square root of 2. But what is the exact identity of that hypotenuse? The square root of 2 is not 1. 1 squared is 1. That's too little. It's not 1.4 squared. That's too little. It's not 1.41 squared. That's too little. So what is it? And as the ancient Greeks discovered, there is no number that when multiplied by itself gives exactly 2. Rumor has it that they took the person who discovered that and threw him off a cliff. What we call an irrational number actually means a non-ratio number. It doesn't mean the number is out of focus. You could look at it that way. But the square root of 2 is called an irrational number. I don't think it's a number at all, but there isn't any regular number that when multiplied by itself gives exactly 2. But what is the identity? There's got to be an exact identity of that length up there. So this is a problem that came up at the objectivist workshop, the workshop on objectivist epistemology in 1969. If things have an exact specific identity, what is the identity of a right angle isosceles triangle of side 1 of its hypotenuse? What is it? You can't say, well, it's about 2. It's got to have a real identity. So that's the question, and my answer is check your premises. So we will return to that after a lot of preparation on our premises. First of all, we need to know, what is mathematics? Well, to answer that, let's use Ayn Rand's power question. You know, the power question. What facts of reality give rise to the need for such a thing as mathematics, or the concept mathematics? And I think we know what it is. It's a man makes a will dividing 100 gold coins among 6 heirs. How much does each heir get? Or how big is the earth? So what facts of reality give rise to the need for such a thing as mathematics? The need to acquire quantitative information, i.e., measurements. So we have to define mathematics in terms of measurement. Ayn Rand characterized it, I don't think she intended it as a formal definition, but she called it the science of measurement. That always troubled me because it's not the science of how to make rulers or how to construct a balance beam scale. It's not the science of how you measure, but it is a science of measurement. It's a science of measurement calculation. It's a science of inferring some measurements from others. You indirectly measure a thing by measuring other things and then applying formulas to it to figure out what the unknown is. The important thing for us is that it's a how-to science, which is the end of Plato here. That's it. If you want to know how to save math from Plato, remember that it's a science of method. And here's Ayn Rand saying that in ITOE chapter 7, quote, mathematics is a science of method, the science of measurement, i.e. of establishing quantitative relationships. So it's a tool. It is not a communion with a perfect mathematical object in another dimension that we can only see with our mind's eye, not with our real eye. It's a tool for calculating measurements. For instance, my examples, if I have 100 coins, how do I divide it evenly among 6 suns? Or to flesh out how big is the Earth, if at noon the sun is directly overhead, when it is 2 degrees away from directly overhead, 300 miles north, how much has the Earth curved over that 300 miles? That's the method that the Greek Eratosthenes used to calculate long before the beginning of the Roman Empire what the size of the Earth was. And he got it within about 70% of the right size. It's amazing. So let's make some fundamental distinctions here that we need in order to proceed. Quantity, numbers, and numerals. Quantity is metaphysical. Quantity exists whether there are any minds or not. Quantity is the amount out there in the world. But numbers don't exist in the world. Numbers are a mental method of dealing with the world. Numbers are epistemological. Numerals, the symbols for numbers, such as the Arabic 3 or the Roman numeral 3 or the word 3 or the word dry or the word tres, depending upon your language, those are linguistic entities standing for numbers. Numbers identify the quantity of things. So I think you have to have that in mind. Quantity comes in 2 kinds, or there's 2 applications of it. Multiplicity and magnitude. Now, those are big words, so I try to shorten them as manyness and muchness. Manyness counts or refers to the number of things. Oh, I said number. The quantity of things. There are many X's and few Y's. Magnitude or muchness is an attribute, a characteristic that can be more or less. Like the green line has less length than the red line. Unfortunately, the word more can be used for either. I had to use less and few, but you could say there are more X's or there's more length. So English is not really making the distinction on the positive side, but it does on the negative side. So let's take the discrete quantity first. Measuring the quantity of things. Here we got 3 things. How do we do it? We say 1 and we touch or point to the first one. We say 2 and we touch or point to the second one. We say 3 and we touch or point to the last one. They have all now been counted, right? A number, a numeral. has been assigned to each one. And what is the definition of 3? The last numeral that we said. It's the name of the number after 2. And 2 is the number after 1. Strange, isn't it? 3, when I realized this, it was a lightning bolt, but now it doesn't sound so boltish. But 3 is the third numeral. 3 is the third numeral. Now, C, the letter C, is not the C'th letter. 3 is the third numeral. It's important because the numeral 3 implies 1, 2, 3. It contains 1, 2, 3. It's defined as a number after the number after 1. So when you say the number is 3, you are matching the things counted with the symbols, with the numerals. A number's place in the sequence serves as a standard of measurement. And then before that, I gave my definition of number. A number is a member of a series of symbols in a fixed sequence used to measure quantity. A number's place in the sequence serves as the measurement. 3 is the third symbol, and then we get to this guy. We were doing so well, and then suddenly this man appears, Bertrand Russell. And for those of you who think that life as a standard means merely physical survival, look how long he lived. 98 years, if I can do math. No? 90. No, but that's not right. He didn't live. Oh, 108, it says. That's not right. It's 1970 that he died. That's what it is. He died in I added 10 years to the scourge. All right. He defines number this way. It's probably you're wondering why I didn't. The number of a class is the class of all those classes that are similar to it. Similar means pair up 1-to-1 with it. The number of a couple will be the class of all couples. No. So what he's saying is 2 stands for the group. I put braces around it to indicate it's a group. Ein and Frank. And my left hand and my right hand. This cup and this saucer. 2, he thinks, stands for the thing. So think about what that implies. So suppose Ein and Frank come walking into a ballroom. 2 has walked into the ballroom. The number 2 has walked into the ballroom. That's what he's saying. Now, here's what I say. 2 stands for the quantity of things in each couple. 2 is the quantity of the couple Ein and Frank, of the class or the set or the group Ein, Frank. There's 2 elements in that group. That's the quantity of them. That's not them. They are not anything mathematical. And the way I understand numbers is Ein, Frank has the same quantity as 1, 2. So each number stands for a standard of quantity. 3, 1, 2, 3. That sound, and those 3 sounds together, that sound 3 implies 1, 2, 3, right? That is the standard for measuring these fingers or for measuring the leaves on the clover or whatever. You measure a quantity by a concrete instance of that quantity. You measure weight in pounds, length in inches or feet. You measure lengths by lengths, weight by weight, and discrete quantity of things by discrete quantity of things. Only the things on the right of that are symbols, 1, 2, 3, and so forth. So like measures like, and the second like that serves as a standard is the order of the symbols, which raises the question, well, what about infinity? And as you may know, I hate infinity. It's an invalid concept. Its origin is in mysticism. It's a religiously infused concept. God is infinite. He can't be limited. I would throw it out. I would throw out the word. Instead, there is something that term is mystically messing up, and that's open-endedness. And Pat Corvini was the one who first used that term, to my knowledge, to refer to what had been referred to as infinite, open-ended. What does that mean, open-ended? It means it can be repeated without mathematical limit. Now, you might think you want to say can be repeated without limit. But no, you can't repeat without limit, because you'll die, you'll run out of paper, you'll run out of markers in the universe, there'll be the eventual heat death of the universe in which entropy goes maximum. So it's not without physical limit. It's that the process of calculation doesn't have an endpoint assigned to it. Now, closed-ended processes do. Count the numbers from 1 to 5. 1, 2, 3, 4, 5. And there I have to stop. So there are some closed-ended processes, but infinity is an open-ended process. It can be iterated without mathematical limit. Here's what Ayn Rand said on infinity. An arithmetical sequence extends into infinity without implying that infinity actually exists. Such extension means only that whatever number of units does exist, whatever number, finite number of units does exist, it is to be included in the same sequence. So when we count the last thing, that'll be the last number. Now, thing doesn't necessarily mean entity there. It could be combinations. But there's only so many of anything. Until we meet Georg Cantor, 1845 to 1918. And guess where he lived? In the same town as Ayn Rand, St. Petersburg, Russia. So he died when Ayn Rand was 13. And Wikipedia says about him the following. Cantor established the importance of one-to-one correspondence between the members of two sets. Yeah, I think that's called counting. Matching, pairing. I don't see I don't know higher math, but I am not impressed by this. One-to-one correspondence is known to every child over the age of 3. He defined infinite and well-ordered sets. Is that what it says? My eyes are going. Between members of two sets, defined infinite and well-ordered sets. He's the guy who brought the infinite and the super infinite, called transfinite numbers, into mathematics and messed it up, or discrete mathematics, and proved that the real numbers are more numerous than the natural numbers, says Wikipedia. Now, some of you, probably, half of you have heard of this. How many numbers are there? Well, infinite number, right? There are an infinite number of numbers. No. The right response is, in whose mind? Now, this is me. This is how we're going to shoot down Cantor. Numbers are epistemological. They don't exist except in minds. In fact, numbers are concepts. How many concepts are there? Oh, infinite. No. There are as many concepts as words that a given person knows. So if you've got a 6-year-old, he may know the numbers up to 100, maybe even up to 1,000, but I bet he doesn't know what an octillion is. And if he does, he didn't when he was 1. So numbers exist only in a mind. They're not up there. That's Platonism. That's why I call this Plato's progeny. The assumption is that there's a world of numbers and we need to know how many it's got. How many numbers you got? Well, Ayn Rand's answer is, how many do you need? But Cantor's answer is, it's an infinite number. And in fact, wait a minute, before I get to Cantor here, I got this cute thing. Just to show you that numbers are not infinite, they're not out there, I created a new one. Just today, there it is. That number has never existed before. Maybe some computer printed out those symbols, but that isn't the same as a number. No mind has ever I will bet my life on that. Oh! No. No mind has ever had that particular combination of numerals before. And you now are looking at it, and you can figure out, well, what would twice that number be? You can work with it. But it's never existed before. It wasn't there in Plato's heaven waiting for me to name it. I made it up. There may not be enough things in the universe for that to refer to anything, but it's a new set of numerals at any rate. Okay, how many numbers are there in anyone's mind? There's so many numbers. Some minds, minds that going back to ancient Mayan civilization, maybe they had 60 children, have none at the beginning. And then you have as many as you figure out. Now you have one more. So here's the thing I was referring to. Half of you probably heard this. The number of even numbers is the same as the number of numbers, says Cantor. The number of even numbers, because if we say 2, I can say, okay, that's number 1. 4, that's number 2. 6, that's number 3. 8, that's number 4. So we can index with the regular numbers every even number. So for every even number, there is a regular number, a natural number. From that, he says the number of numbers, even numbers, and the number of regular numbers, integers really, is the same. But that presupposes infinity. It presupposes an actual infinity, and he knew it, and he was happy with that. But the answer to that is, in nobody's mind are they the same. Nobody, however many numbers he knows, has the same number of even numbers and numbers. It's impossible. So this is, again, the idea, oh, well, the numbers are there. The numbers are there and they're infinite. So if you've got an infinite supply of even numbers, you can always match one to one with the regular total set of numbers. But they don't exist out there. They only exist in here. And in nobody's mind are they the same. So that's complete garbage, complete nonsense. Every mathematician in the world, except for maybe 3 of us, believes that the cardinality, the size of the even numbers, is the same as the size of the regular numbers. And his other contribution was that there are more real numbers than natural numbers. There are no real numbers. There are no real numbers. Now, this is the one place where I might be wrong, but I'm telling you my predilection until someone beats me down on that. There are no real numbers. 1.333, to take an easy case, 1 1/3, 1.333 ... is not a number. To be a real number would be to have an infinite number of 3's following that. And you can't do it because there aren't. There's only the number of 3's that the most obsessed person has ever put on there. That's not a number. ... You know, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, you should start with 0 to get 10 numerals. I didn't hear ... in there. It is not a number. 1.33 1/3 is a number. And that denotes the quantity of a third. It's just like a phrase is not a concept. I say, dogs that don't wear leashes on Sunday. That is not a concept. That is a phrase. So 1.333 and so on is not a number. It's an expression. In fact, there are plenty of regular things that are not numbers that you might think are. 2 + 2 is not a number. It's an expression. 17 times 2 + 3 is not a number. It's an expression. It's a direction to perform certain operations. It works out to be 37, which is a number, but it isn't a number. It's an expression. 5 squared is not a number. 1.33 ... is not a number. Now I'm going to walk back, as we say now. I'm going to walk back my hatred of the real numbers. Maybe they mean something number-like. Maybe there's a point to them. Maybe there's a purpose to them. But they aren't numbers. And that's very important in making mistakes like the real numbers are more numerous than the other numbers. And they're different orders of infinity. The reals are a different cardinality than the naturals. Cardinality is the amount of them, the number of numbers. To show you that 1.333 is not a ... is not a number, what's the next number? What's the next number after 1.333? Is it 1.331? 1.3318? 1.3336? There's no way to know. In fact, Cantor makes hay out of that with his celebrated diagonal argument. Numbers are counters. They quantify by providing a standard amount that you can match with what you are counting. ... prevents that. It's not a number. Now, fractions and decimals are numbers. Fractions are subunits. 1/5 is followed by 2/5 is followed by 3/5. You're just taking a smaller unit. You know, I should have done twelfths because you could count 1 feet, 2 feet, or you could count 1/12 of a foot, 2/12, which is 1 inch, 2 inches, 3 inches. So it's a smaller unit. And the decimals are just fractions with 10 in the denominator, powers of 10 in the denominator, notated a little differently. So you know what comes after 0.1, 0.2, and then 0.3, which is the same thing as 1/10, 2/10, 3/10. They're well behaved. When you talk about well ordered, these are well behaved. So the real numbers are supposed to be actual infinities. They're points on the real number line. There is no real number line. They're points on the real number line. They have infinitesimal zero width, but somehow they are there on this made-up thing. So I ask, what can so-called real numbers do that decimal numbers can't? Decimal numbers are our friend. Decimal numbers can get as precise as you are capable of being in measurement. Math is a tool. Don't you get that kind of sense when he says, you know, the infinite set of integers and the infinite set of reals are not? Don't you get the feeling that the idea that, hey, we want a hammer and a screwdriver for calculating, so to speak, that's been lost. We're back in the realm of math reveals another world, a world of the mind that, you know, is in touch with something beyond lousy physical matter. So how do we measure the continuous now? We left the discrete. I hope I put the infinite to rest. And we're turning now to the other big category, the muchness. How do you measure the continuous? It's by counting intervals. So I made some intervals, and they're, you know, just hand drawn. I didn't use a ruler or anything. I took that same line you were looking at here, and I put in 6 more or less uniformly spaced marks. And we count them. Now, here's the problem that comes up. There's something left over, and there's almost always something a little bit left over. Ayn Rand answered that so-called problem in the workshops. After John Nelson of the University of Colorado was arguing, but you can't be perfectly exact because there's always some left over. If you take a smaller unit, you extend your decimals, there's still a little left over. And she says, isn't there a very simple solution to the problem of accuracy? You can always be absolutely precise simply by saying its length is, I wrote that in because what she actually said is simply by saying no less than 1 millimeter and no more than 2 millimeters. That's an interval. So when we're measuring this length and counting intervals, we get a length between 5 and 6 of these intervals. Precision is contextual, not platonic. There is a minimum interval. I call it the cent. Because the cent is our monetary minimum interval. You can calculate out, fractions, but when you pay somebody, you can't get smaller than 1 penny. We don't have anything smaller. Less than the cent, I call nil. And that's one of the most important contributions I've made here, I use that symbol, like approximate zero, effective zero. Nil is what is negligible, but still there. So if we go back to this one, if the cent is 1, the length here is 5 plus nil. With that, we can solve the question of what is the exact identity of the hypotenuse. With that in a little physics. Check your premises. The premise is we have a mathematical tool that can be expanded or shrunk, but that doesn't mean a thing in reality can be. There is, in reality, apart from man, no infinitely scalable line. No infinitely scalable line. Yet that's the premise of the problem, the alleged problem. Math scales, you can always get, 1.4, 1.41, 1.414, and I forget what the next number is. You can always get zoomed in further and further and further, but reality does not scale. So all of the sides could be 1 micron or 1 light year. Doesn't matter for the math. I just said 1. You can write whatever unit you want there. In reality, if you zoom in, look what happens. Oh, it isn't a straight line, and it hasn't got a sharp edge, and that right angle isn't a right angle. Math scales, but reality does not. Here's Earth and the moon from 30 million miles away. The reason why the moon looks close to the Earth is that it's gone around it. If you looked at it straight head on, it would look very far from the Earth. It's 250,000 miles, and the radius of the Earth is only 5,000. So that's not relevant. Here's Anaheim from maybe 3 miles away. Here's where we are from maybe 30 yards away above. It's Google Earth, so it's above, but that's the thing at the top there. Oh, I got a laser pointer. I have to use this. This, I don't know which one I should. That's the tower we're in, the Oasis Tower. And this, talk about not scaling, 3 angstroms, which I think is 10 to the minus 10th. It's either 10 to the minus 10th or 10 to the minus 9th. 10th, someone says. It's not the same. It's not the same. If you have a real thing, you zoom in, and it won't be the same. Here's a rational measurement calculation for any real right-angled triangle, isosceles. If you take your C, your cent as 1, the exact length is between 1 and 2 of the hypotenuse, because 1 squared is 1 and 2 squared is 4, and the square root of 2 squared is 2, and 2 is between 1 and 4. It's not very good. So take 1/10 as your minimum interval. Then you can say the exact length by that standard of the hypotenuse is 1.4 in the middle between 1.4 and 1.5. I use a double underscore to mean between. I know you can use those angle brackets, but they don't speak to me. If you square 1.4, you get 1.96, and if you square 1.5, you get 2.25. Well, 2 is in there. And if you just go one step more, you say the exact length by a higher standard, if we can measure to 0.01 of a unit, is 1.9881 to 2.0164. That's very close to 2. Now, it's not that that's better. You may only care that it's more than 1 and less than 2, that hypotenuse. It's not that the cruder ones are more are inferior. Well, I said I would cover limits, but we are out of time, so I can do that in the question period. I just want to get to the conclusion. Math models reality. Mathematics has to live up to reality, not the other way around. Math models reality to serve its masters. Physics, engineering, and finance. Arithmetic had its origin in trade, in people needing to know how to keep the books. Math is the servant of purposes in reality. It is not relationships between forms in the sky that the mind can't get around, the mind can't grasp. So here's my summary slide on this. Mathematics, almost as good as the real thing. There's a circle used to model an apple. The apple is perfect. The circle is an approximation of the apple. It's good to have. And what you see, x squared plus y squared equals r squared, is the algebraic linear algebra formula for a circle. The apple is the real thing. The tool of measuring it is a very good tool, but it is not the real thing. Thank you. We'll take questions. Yes, Debbie?
Yes, you mentioned if one is curious about what you had to say about limits to ask in the question period.
Thank you.
I'm asking about that.
I'll pay you afterwards. Thank you. Okay. Limits gets to be a little bit more difficult when you get to continuous magnitude, the muchness. But let's take it for manyness and look at series. I didn't make the nice animation for this, but just go through it. Here's the series: 1 plus a half plus a quarter plus an eighth plus a 16th plus ... Now, it's okay to have a ... if you just mean and as far as you can go. And it's not, this is not one number. This is a series of numbers. And you say the series continues. So there, the ... just means and more numbers are coming. So the traditional way of doing this is really cute. I like it. You multiply this equation by 2, and you get 2s equals 2 plus 1 plus 1 half plus 1 quarter plus 1 eighth plus 1 16th plus 1 32nd. But the right-hand side here is the same as the series. You see that? Multiplying it by 2 just sticks a 2 in front of it. So 2 times the series, this, equals 2 plus the series. So if you subtract s from each side, you get s, the sum, equals 2. Cute. Now you really understand something, right? No, it gives you no understanding whatsoever. So here's my way. 1 plus a half, blah, 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 blah. Well, these two are 1 1/2. Then the series up to there, oh, I wrote it wrong. It's 1 3/4. And then it's 1 7/8 if you add it up. Then 1 15/16. I can see that at some point it's going to get less than the minimum interval. So that's 2. So no matter what standard precision you use, no matter what the minimum interval is, the sum will reach it. So the sum is 2 minus a negligible amount. It's 2. 2 is the limit in the sense that you can always get to less than your minimum measurable interval of 2. So that's the limit. James.
You brought up a couple of geometry examples. Do you consider geometry to be part of math or part of physics? Because Ron Pizzaturo brought up the idea that it's actually part of physics because there's a physical subject matter, and like other parts of physics, geometry simply describes those facts mathematically. What's your view on that?
I like Ron Pizzaturo's approach to numbers, but I've never understood why geometry would be different, except that it handles continuous magnitude. So I do not exempt geometry from math, and they're intertwined historically. The first breakthroughs were in geometry, not in math, in arithmetic or numbers. So no, I don't go along with that. But I'm willing to listen.
Well, I'll try to convince you after.
Okay.
How valuable would you say graphing functions are in solving problems and thinking about the law of identity as it applies to like a domain and range for those functions?
I couldn't hear all that. It's my hearing. It's not your speaking, but say it louder.
How important to solving problems in math would you say graphing functions are? Specifically, do you apply the law of identity to like the domain and range of a function?
I think I'm glad you asked that, because there's an important distinction between calculated value, where you can take it as far as you want, and measured value. You only bring in the interval at the end. When you do the calculations, you may have noticed, if I can get back to it quickly, I'm not sure I can. Yeah, there it is. Here, I said the minimum interval was 2 decimal places, and on the right, I've got 5 decimal places for each. You can go as far as the math will take you, and as you need to, in the process of in the middle. But when you come out, you have to have something that has error bars, as they call it, around it. It's the same as imaginary numbers. Imaginary numbers are based on the square root of -1, which doesn't exist. There's no square root of -1, but it's an operator. It's not really a number. And in the middle of a calculation, you have a complex number which is part real and part imaginary, like 1 plus I or 5x plus I. But at the end, you've got to have something without an I. So in the middle, you can do whatever is necessary to get the result that you're looking for. It's only in the end where you bring in the minimum interval. So as far as you'd like, as far as makes sense to go, that's how far you go with the linear algebra, I think is what you're talking about.
Thank you.
Thanks.
We have a question from online.
Okay.
What do negative numbers represent in reality, and how much mathematics is eliminated if you don't allow real and complex numbers?
Oh, I allow complex numbers. They're not numbers. They're expressions of a number and an operator. Real numbers, I thought I had a slide, but I don't recall going through that, asking what can real numbers do that decimals can't do? And I'm not aware of anything. So I don't think that it would eliminate anything in math. Certainly, transfinite numbers and the Cantor set stuff. I looked on the web. Nobody even claims it has any practical implementation, except about other theoretical issues. But they don't even try to defend it on practical grounds. Now, negative numbers are differences. Negative numbers are relative negative. They're not absolute negative. There's no such thing as negative quantity. But the simplest illustration of how children use it all the time, they're playing a game, let's say baseball. My team is 3 runs behind. That's a negative number. Our team is -3 in relation to the other. So it's a difference between one number taken as the standard and the number in question, which is behind that, which you have to count backwards to. So it is a completely valid phenomenon, but it is not the primary meaning of number. It's a derivative because it involves a difference. Okay?
I think that this talk was better than the one you gave last year. So I'm excited what you will deliver in a few years on this topic. So my question relates to infinity. Is there any length physically that is the shortest possible length? And that may sound like a question of physics, but
Yeah.
it's a parallel to epistemology and maths, because if there is, then the number of quantities between 0 and 1 is infinite actually, not only potentially.
Yeah.
Or so I would like to
I
hear
want to say
some-
2 things. Let me say 2 things. Some people like to talk about potential infinity. Infinity exists as a potential, but it's not a potential in the way that you have the potential to learn the piano. That's something that could become actual. I can do this. I have the potential to do this. If I enacted certain causes, the result would be I'd be doing this. But infinity, you will never get to infinity because it isn't a place. It's a process of adding one more. So in a way, infinity is always actual. If you take it as there's a process, there's a loop, you can circle around again, taking the previous output as your new input, iterating, you're actualizing what infinity means. But it's not like, oh, now I've gotten so big a number that I'm at infinity. You will never, it's not potential in that sense. And the other thing is the shortest distance. Yeah, I think there is a shortest distance, but that's a physics question. And here's the interesting aspect of that. I don't think I can get back to the slide, but you remember the angstrom scale with the 3 lights? They can't actually photograph a molecule, but they did something that bounced something up, probably electrons off the molecule. And if you look at it, it's bright in the center, and then there's a kind of fringe around it. That's because it's vibrating. All molecules are vibrating. If they weren't, they'd be at absolute 0 temperature, and there's a physical reason why you can never get to absolute 0. So all molecules are vibrating. Things that are in motion are not at a place. This is one of the things that Ayn Rand said in private conversation that made my jaw drop. She said about a thing in motion isn't anywhere. An economist said to her, I think, a thing in motion at any given instant is somewhere. That's A is A. No, she said it isn't anywhere. It's in transit between 2 positions, but position is for something at relative rest. If it's moving all the time. There are no instants. That's an infinity of a division kind, an infinitesimal. There are no instants. An instant really means a very, very small interval of time. Okay? So no matter how small you make the interval of time, the molecule has moved somewhere. It's not at rest. So there's a shortest distance of, I think, implied by that. I also think that it may imply the Heisenberg uncertainty principle. Maybe the Ayn Rand came up from philosophy with the Heisenberg uncertainty principle, because it sort of relates velocity to size. And she thought the size was, James is just shaking his head now. It's the technical thing is h bar equals either eta nu or momentum times position. But it's kind of the same thing, that you cannot locate a thing that's moving as if it were not moving. It's always changing its position, and there's limits to how narrowly you can specify the time interval and the space interval. Let's hope, that would be a big feather in her cap if that's right. But anyway, I think, yes, there is a shortest distance, but that's physics.
Yeah, but wouldn't that contradict open-endedness of numbers? That there is actual finite number of numbers between 1 and 0. Yeah.
Yeah, I think there are.
So
I mean, you could pretend that you could get half of this shortest distance and see what follows from it. But you can't come out with that as a measurement in the end. That's the difference between calculational methods and actual measurements.
Okay.
The
Thank you.
measurements have a limit.
Yeah, thank you.
What would be your response to Immanuel Kant, who believed that mathematics is a proof that synthetic a priori reasoning basically is possible?
Well, you can't accept the whole analytic-synthetic dichotomy. That's a complete destruction of the concept. But I never understood why he thought that, I think his example of 5 plus 7 is 12 is synthetic. I would think that's analytic, if anything is. And a lot of his successors thought that was analytic. But to ask, was Kant mistaken about that when here's a guy with a sledgehammer smashing into every truth he can find, was he mistaken about A, is a question you wouldn't ask. It doesn't even arise. So I think we don't have any more time, because time is finite. So thank you very much.